Hello. So today we'll explain what we have learned and what we have been working on over the past months during our internship at the Barcelona Supercomputing Center alongside the Computational Earth Science Research Group. Our task was to improve a Python package providing multiple standardized interpolation methods for atmospheric chemistry models. But before talking more about our project, we should probably start by introducing what interpolation actually is. So, according to the Oxford Languages, interpolation is the insertion of something of a different nature into something else. This is a rather linguistic definition, but it kind of still holds in a scientific environment. Imagine you have a set of data, for instance the temperatures in cities along a straight road. We may then want to know the temperature in a city where no measurement is available. Determining the data given the known points is called interpolation. Of course, one could also perform interpolation in multiple dimensions. If, for instance, a grid of data points is known, we may use this grid to determine some missing data points. We may even use it to determine an entirely different grid. This is what we reference as horizontal interpolation.
Interpolation can also be carried out in a vertical manner. In this case, we want to calculate the value at a point whose altitude lies between two different vertical levels. So what you're seeing here is a 3-hour report of atmospheric dust concentrations over Southern Europe and Northern Africa. This model was generated using the Monarch model, which was created at BSc. By running the model output through the Interpolation tool, we can produce a model that has a higher resolution, and it can also be converted to a different grid that may be more useful for any future analysis. So if I quickly motion to this diagram, say we want to find the value of some variable, like atmospheric dust concentration, at this red point. What we do know is the value at many nearby points, and we also know their positions with respect to the point of interest. So using this, and also whichever interpolation model you decide to go with, you can assign what's known as a point weighting, represented by lambda, to each nearby point. Essentially, a point weighting determines how much of an influence, or how much of an impact, each point is going to have on your final estimation. For horizontal interpolation, we use the inverse distance weighting method. And in this case, the closer a point is to your point of interest, the more of an influence it's going to have on your final estimation. Vertical interpolation works a good bit differently in this case, where we use the cubic spline method. The cubic spline method fits a cubic polynomial in a piecewise manner between all the different vertical levels. And this can work very, very well for vertical interpolation because commonly our points of interest lie very cleanly between two distinct vertical levels in the atmosphere.
Now we can talk more about the tasks we worked on during this summer. The first task we worked on was adding pointwise interpolation. In the beginning, the tool was only able to interpolate from one given standard grid to one other given standard regular grid. We tweaked the tool such that one could also interpolate to a given set of data points instead. Another one of our tasks was to solve a freeze bug. This unfortunate bug happened when both the horizontal and vertical interpolation flags were active. In that case, the problem would encounter a deadlock and would thus never terminate. We managed to locate the error. The cause of the bug was a conflict between the MPI4Pi library and the multiprocessing library. Indeed, the freeze bug appeared as soon as a multiprocessing pool was followed by an MPI scattering and followed again by a multiprocessing pool. This layout, of course in a more complex manner, would only appear when both the horizontal and the vertical flags were active, thus causing the deadlock. Sadly, we didn't find a magic solution to this. We ended up serializing the multiprocessing part instead, though.
Our third task was to reverse the order of horizontal and vertical interpolation in the tool. Originally, only vertical interpolation was made parallel, but the idea here was that by reversing the interpolation order, we could take advantage of the MPI processes that were used. And in doing so, the horizontal interpolation would also be parallel. Ideally, this would improve the overall performance of the tool. Sadly, this didn't quite work out as we'd hoped. The horizontal interpolation in the tool relies on some files that get created and saved at the beginning when the tool is initialized. This is done to save memory. But as a result, we came across some indexing problems later on when the data is split across different processes using MPI. And typically this is fine. and you could use something like a NumPy mask, for example. But unfortunately, we couldn't get this solution to play nice with MPI, and the system would suffer a memory overload, killing the batch job. Now, a lot of the work is done in terms of structuring this change, but some extra time will be needed to debug this memory problem before we can properly get the tool running in this fashion. So that's it. Thank you for listening, and before we go, we'd just like to give a quick special thanks to our mentors Francesco Benincasa and Kim Seradell. We'd also like to thank everyone at BSc for being so friendly and for making us feel so welcome during our time there. Finally, of course, we'd like to thank Leon Kos and everyone at Prace for providing us with this opportunity. It was a great learning experience, and we really enjoyed our time spent over the summer.